Right, you saw the title, so I'm not going to do any long intro or anything like that. This video will tell you about all of the things about how to transition from a language like C# or Java into C++. Now, this video is not going to go over the basic stuff like, how do I print to the screen? You can just Google those little things. But this video will cover the more complicated things you will face and be very confused by when you hop into C++, coming from a more managed language. Okay, enough of that, let's play the intro. Okay, don't copy down any code I type, just watch the video since a vast majority of this is theory-like stuff. Right, let's start it off with the compiler and linker. So, we all know what the compiler is, I won't get into that. But what about the linker? Well, in .NET and Java, the linker isn't something you hear about. Because everything is managed, we don't need one, or at least the one we do have is built into the compiler, so you never see it. The most important thing that you need to understand, and this especially comes in play on the next topic, is that to the compiler, all of the files in your project are separate. So let's say your project is split into 3 files. The C# compiler would essentially look at all of those files together, and it will work out what refers to what. All of that happens within the compiler. However, the C++ compiler doesn't work like that. It takes one file and turns that file into an object file. And it does that for each file. So now, if you look at this, we have 3 compiled files. So the code has essentially been compiled to machine code, it's just that they've all been compiled separately. But this is one big application. So how do we now join all of these files up into one big executable file? Well, that's what the linker does. You just give the linker a list of object files, and it will put them all together. Now, sometimes libraries come as object files, and these are called static libraries. So you just link in the library, and then the library itself essentially becomes a part of your final executable. Static libraries don't exist in C# because, well, there's no linker. C# has dynamic libraries, as you can also get in C++, which means they are separate from the executable file. So, for a C# program, as it runs, it would read through those DLLs to find the method it wants. This is one of the reasons why C++ can be faster than a language like C#. Okay, well, this brings us very nicely onto header files. So, if these are all separate things, how do we refer to something in another file without the compiler giving us an error? Let's say I define a class in the myClass file. If I want to refer to that class in the program file, how would I do that if they're all separate? Well, what we do is we use header files. So, let's actually look at a project that's laid out like this. Now, I'm using Visual Studio for this video, but obviously use whatever IDE you want. As you can see, if you look over here, the project is split into 3 files. And in our program file, we are referring to a class called myClass. MyClass is defined in the file called, well, myClass, and it contains 2 methods within it. One adds 2 numbers and returns the result, and the other just returns 3 because I'm clearly very creative. Now, as we might expect from what I just explained, trying to access this class from outside this file, like in the program file, gives us an error, because each of these are compiled separately from one another. So this program file, when compiled, won't see anything outside of it. So we have to think a bit differently, because we can't make a class like this. So firstly, what we need is a header file, which is a file ending in .h. Sometimes you can also end it in .hpp for C++ projects, just so you can distinguish between C header files and C++ header files. So, something like this. And within this header file, we make an outline of our class, myClass. And what I mean by outline is that we don't include any of the code, just a list of all of the members this class will contain. So the outline would look like this. Now, anywhere that we want to use myClass, we have to include this header file. So, within my program file, I'll add an include for myClass.h. This include here is nothing special. In .NET or Java, there's a lot going on when we use things such as using, but in C++, literally all include does is it copies the contents of the myclass.h file and slaps it right here. That's literally it. So it looks for a myclass.h file, and if it finds it, it takes everything within that header file and it puts it here. If it doesn't find one, then that's a compiler error. So technically, I could actually just copy and paste the stuff inside the header file, paste it in here, and delete this. And this is identical to using the include. That's why it's a preprocessor definition, which you can see by the hashtag here. It copies across the data from the header file first, and then everything gets compiled. Now, there are actually two ways of using the include declaration. One is with quotes, like we just used, and one of them is with angle brackets like this. And you usually use these to access some kind of system header file. So for example, if I want to use the Windows header file, which contains an outline for all kinds of methods for things such as opening windows that of course later on get linked in, then I would write it with angle brackets. What these technically mean is the angle brackets, generally, this is in most compilers, will search for this header file in the system directory first, while the quotes will search in the local project directory first. So in this case, the quotes will search in the same folder as the program file. Okay, now this header is only half of the solution. We've made an outline of the class's members, but now there's an issue with this. We are now declaring this class twice, once in the header file and once in the actual myClass file. We can't do it like that. So let's just delete all of this and we'll keep hold of the methods. Now, this alone isn't enough, because all we're doing here is we're making two methods that are outside of a class, which is actually possible in C++. You don't need to have methods inside classes. What we need to do is we need to say that we're providing the code for these within the myClass. And to do that, before the method name, we write myClass and 2:, just like this. Now, of course, that's going to give us an error, because as far as this file knows, there isn't a myClass. So the final step is to just include the myClass header file. That way, C++ can recognize what myClass we're providing the code for. So this is how you make a class. You outline all of the members in a header file like this, and then within a C++ file, you actually provide those methods codes. So now, when this file gets linked in, it will fill in these methods bodies. Okay, let's move on to one of the most fundamental concepts, the pointer. So, a pointer is a small object. It's just like any other object really. In 32-bit machines, it will most likely be 32-bit. And in 64-bit machines, it will most likely be 64 bits. Typically, a pointer is nothing but an integer. But the reason we distinguish a pointer from a normal object is because of what it does. Quite simply, it points towards a specific location in RAM. So let's pretend this line here is our RAM, and it's split into each of the bytes. Let's make a pointer that points towards position 3. If we were to look at the bits that make up this pointer, it's just a 3. But what we can do is we can dereference this pointer. So that means we take a look at position 3 in the RAM and see what's there. In C++ and C, and even in unsafe C#, you can represent a pointer type by writing the data type you're pointing at, followed by a star. And to generate a pointer towards something, like a certain variable, we can use an ampersand. Let's take a look. And all I'm going to do is make an integer called a. So there are no pointers here or anything like that yet. Then I'll set it to 7. So exactly like you would normally do in C# or Java. Now this number is of course somewhere in the RAM, right? Well, what we can do is make a pointer to that position, to the place this 7 is in RAM. So let's do it. So this will be an integer pointer, because it's pointing towards an integer. What that int here really means is it's going to point towards the RAM in 4-byte intervals, because an int is 4 bytes big. So if I push this pointer forward by 1, it would move forward by 4 bytes. Now, let's call this b, and finally, we will now make it a pointer to the variable a, just like this. So, this ampersand, as I said earlier, will make a pointer towards the variable a. So now, we have a pointer to the variable a. We'll play around with these two in just a moment, after I cover a bit more theory. Now, what happens if I write b++? You might expect it to increase our number 7, right? because B is pointing towards that 7. Surely, it would take what it's pointing at and increase it by 1. Nope. What B++ would actually do is it would add 1 not to what the pointer is pointing towards, but to the pointer itself. So if we imagine our variable A is at position 20 in RAM, instead of increasing that 7, the pointer itself will move up the RAM by 1. Now, since it's pointing towards an integer, and integers are 4 bytes big, it will technically jump forward 4 bytes. So now, it's pointing towards position 24. Yeah, that didn't increase our 7. If we're not careful here, and we try to set at the position this pointer is at now, we can potentially corrupt some stuff that we didn't want to corrupt. Don't worry, you generally can't access memory outside this application. So the worst you'll do is corrupt your application's current memory. But of course, it's still not ideal. So we don't want to increase the pointer. We want to increase what the pointer is pointing at. And in order to change the value the pointer is actually pointing to, you have to dereference it. I mentioned this earlier. So to do that, you just write a star before the pointer. So if I wanted to change the 7 into a 13, I can just write star B equals 13. That's dereferencing and setting that dereference value. So, with all of this knowledge, let's play around with some things in C++ and explain why they work that way. First, let's dereference and increase variable B. What will the value of A be? And what will the dereferenced value of B be? Alright, let's take a look with a little bit of debug. So, the value of A has gone up to 8. Of course it has. The pointer B was pointing towards variable A. So when we dereferenced it and incremented that by 1, we pushed whatever it was pointing at up by 1. And it was pointing at A. Let's put our mouse over B and whoa! Now, I know this might look super overwhelming. I mean, what is this number? But it really is quite simple. This is the value of the pointer itself. So this is the position in RAM that the pointer is pointing towards. This is where in our RAM the variable A is stored. Makes sense, right? But we don't want to look at the pointer itself. We want to look at the actual item it's pointing towards, so we need to dereference it. Thankfully, the debugger will usually let us look at it dereferenced. In Visual Studio, it's simply by expanding it out like this. Of course, this may vary by your IDE. The next thing you can also do with pointers is look at a certain offset ahead of them. So, if I have a bunch of integers in RAM like this, and I just want to look ahead of where this pointer is, I can use square brackets, kind of like you normally would with an array. So if I write square brackets 3, then that will look 3 places ahead. And this is dereferenced, so this does actually look at the value 3 places ahead. This doesn't change the pointer, it just gets the value. Now, why are pointers so essential to C++? Well, let's take a look. Here I just made this completely random class. Don't worry, I'll talk about the syntax of how you write classes at the end. This is just to demonstrate. Within this class though, you can see that there are 8 integers. Now, there's a thing in C++ called sizeof. That tells you how many bytes big a particular data type is. So why don't we find out how big our class is, like this. We can predict that this will give us 32, because integers like this are usually 32 bits or 4 bytes, and we have 8 of them. So our class here is going to be 32 bytes long. 8 integers. And just to prove that, take a look. A is set to 32. Our class is 32 bytes big. Let's say I now made a method. Let's call it my method. And this takes in our class. This is bad code right here instantly. This method is asking for our class. That means the entire 32-byte class. Unlike in C# or Java, where it's basically just passing pointers around to your classes internally, this is literally taking the entire 32-byte class. Let's make a variable A that is of our class's type. So this variable will store my entire class. Then I'll pass this A into my new method. Now, yes, this is actually initialized. So this isn't null like in C# or Java. This is actually initialized, and I will get to that later. That's an important point for later. Now, look at what's happening here. I'm now giving my method an entire copy of my class. I'm taking all 32 bytes of it and copying the class across. Think of how wasteful that is on both the CPU and our memory usage. So I now have one copy of the class in the variable A and another in the variable CL. We are now using 64 bytes of data for the same object. However, we can fix this easily. Instead of making this take in our class, we make it take in a pointer to our class. So now, instead of carrying our entire 32-byte object, the only thing it will carry around is our pointer. And all the pointer is just a 4 to 8 byte number. You can imagine that that's much more performant than passing a copy of the entire object around. And this is why pointers are so essential to C++. They are important for performance, and they help you keep references to things as opposed to copying things. Okay, I've made a lot of changes here. Now, you know how I kept on saying that it will make a copy of the entire class? Well, you have to be careful, because if the class contains pointers, those pointers will still point towards the same thing. Here, I have two classes. The first class is still just 8 integers, but the second class has a pointer towards the first class. I also have two variables here, A and B. And once again, unlike in C# and Java, I don't need to initialize them, and I'm changing the first class pointer variable in variable B to a pointer to my first class. So pause the video now if you need some time to work out what's going on, and then I'll move on. Right, and now I've got my method here that takes in the second class, not a pointer to it. This is important. Let's take the first class pointer's first integer within my method and change it to 14. Right, firstly, let's stop right there. What is this arrow? Well, it's literally just dereferencing a pointer and accessing a member on this. So we need this because if we look within our first class, the first class pointer is a pointer. So in order to access the values on the first class this is pointing to, I have to dereference it first. And the arrow just dereferences it while also accessing the members in it. It's the equivalent of writing this, essentially. Now, here's the question. Will variable A change? So will the first integer in variable A change at all? And even further, will the first integer in the first class pointer field in variable B change at all? Keep in mind that this right here is not a pointer to the second class. Now, the answer is actually yes, it will, which might be a bit confusing because if I don't make this a pointer, surely it's copying across the object. Yeah, you're right, it does copy across the objects. It will copy all of the members within the second class. Now, the second class only has one member in it. What is that member? It's a pointer. What did I say right at the beginning a pointer really is? A pointer is essentially just an integer. So when we copied our second class, all we copied was the pointer itself, not the value it was pointing to. So that means it points to the same class, the same instance of that class, as the variable A. So the pointer itself, the 4 to 8 byte pointer, has been copied, but it's still pointing to variable A. And this is so important to understand. This is why languages like C# and Java are so easy by comparison. And there's one more thing I just want to quickly mention. There's also something called void pointer. And it's basically where it's pointing to something, but you have no idea what it's pointing towards. So it's kind of like the equivalent of objects in C#. Now, you can't do anything with a void pointer. You have to cast it to something else if something does give you a void pointer. Because how is a compiler supposed to work with that? When you write this, how does the compiler know how many bytes to move forwards when you increment that pointer? It doesn't. So that's what void pointers are. And when a method gives you a void pointer, it's essentially expecting you to cast that over to the correct type of pointer. Alright, now let's move on to the heap and stack. So, the heap and stack are the two important blocks of memory in your RAM. One of them is super simple, and one of them is fairly complicated. Let's start it off with the stack. The stack is exactly what it says it is. It's a bunch of items all stacked on top of each other, and normally you can push and pop from the stack. That's all it is. It's literally just a list of items. You can't remove from the middle of it though, and that's quite important. You can only really remove from the top of it. Now this is important. The stack will lose all of its items when we leave a method. So let's say within a method we added 4 items to the stack. When we return from that method, those 4 items are automatically popped off the stack. That's called the stack frame. It's the current section of the stack that is dedicated to just our method. So as soon as we return from whatever method this stack frame is for, that entire frame gets removed. So what actually is the stack? As in, where does it come from? Is it provided by the operating system or what? Well, it doesn't really come from anywhere. Essentially, when you compile your applications, it will generate instructions that pushes and pops to this stack. There's no built-in function to the operating system that does that or anything. Your code itself, when compiled, will contain the correct instructions to do things in the stack. Now, I was originally going to show you the decompiled instructions of our application at this point, but I decided that it was a bit much. So let's not do that. But if in a future video you would want me to take a look at a much deeper dive into stack and how it really works, and start looking at the compiled instructions that make the stack become a thing, then please tell me. Okay, now what data actually goes on the stack? Well, any local variable, that's it. When you make a local variable, it goes onto the stack. So if I write int a equals 20, that's putting the number 20 onto the stack. That means if we made a pointer to a and we tried to return that pointer to another method, we would probably get a garbage value because it's been popped off the stack. And literally any local variables you make will go onto the stack. There's also some extra data like the return address that automatically goes onto the stack. So that way when you return from a method, it knows exactly based on the stack which instruction to hop back to, since it is right at the bottom of the stack frame. And it also puts the position of the last stack frame in there too. And other things that go onto the stack will be all of the arguments and the return values of the methods and things like that. So technically it's not entirely local variables, but from what we can see in our code, and from what you really need to know, it is just the local variables and arguments. So this is why there's an issue with passing around entire objects. When you pass an object around directly like this, that object is going onto the stack. However, if we pass a pointer to something, then only that pointer will get copied across the stack, as opposed to the entire object. That's the difference. Alright, this now brings us onto one of the differences between C++ and a managed language like C# or Java, which I actually talked about quite clearly earlier. I have a class called myClass. Once again, at the end of the video, I'll get into the syntax for all these things. And then I do this. So, I make a local variable of type myClass in some other method. Now, in C# or Java, that variable a will be null, won't it? We haven't initialized it yet. In C++, that is not the case. This variable has just initialized itself onto the stack. So after this line of code, a is now on the stack. Now, if I add a constructor to my class, so let's say that takes in an integer and sets that integer, then I can call that constructor down here by writing the brackets after the variable name and providing the arguments. Yeah, I know this is quite different from in C# or Java, but it still makes sense because it's instantly initializing the class, so we have to be able to provide arguments to a constructor, and this is how we do it. Okay, let's slightly modify this here. I've added two methods. Take a moment to just get familiar with these two methods. Okay, now, I'm going to show you what's happening on the stack in this code, just to be sure that we absolutely get this idea down, and we don't have to think about it again, because as we get into the heap, you'll need to already have a very good idea of how the stack works. Okay, now let's have our little stack here and change it as we run. So, this is our stack, and this little outline here is our stack frame. Let's go. So, when we run this line of code, what we're going to do is we're going to make an instance of my class. Now, in this scenario, my class is actually a good 16 bytes, as we have 4 integers in it, but that size can vary, of course, based on the class. So, when we create our variable a, we are adding that to the stack. And that's it. No pointers are involved here or anything, that's fine. Then, we call the second method, and this method takes in a raw myClass parameter. So, C++ will put in the extra data it needs, such as the return address, and we change the stack frame, and we now have to bring in the parameter, which of course, since we aren't pointing to it or anything, will involve a copy of the entire object like this. So now, we have the same object twice. Then, we take our second object and we change the integer within it to 123. And then we exit that method, we then remove that copied object off the stack frame, use the extra data provided to us to help us adjust our stack frame and point the program to the right address. And since that is now well out of our stack frame, it has essentially been popped off the stack, and that class is gone. So technically that was completely pointless. We modified an object that would just get popped up for later anyway. However, if I made the method take in a pointer like this, it would be different. Remember that I'm using an arrow here in order to dereference and access members all in one. So now if we look at the stack, when we run this line, we add our myClass object onto the stack, and then when we go into our method, we make a pointer towards that object and put that very small pointer onto the stack. So now, when I modify that value in that pointer, it's modifying that item on the stack. Alright, I think we've definitely gotten the concept of the stack down. Next, let's focus on the heap. So, what data goes onto the heap? Well, for every single line of code we've written so far, nothing has actually gone onto the heap. I'll get into how we put objects onto the heap, but I want to explain what the heap actually is first. So the heap is a bit smarter than the stack, but more complicated. Before we look at how it roughly works, just like with the stack, where does it come from? Now, unlike with the stack, the operating system actually provides the heap. Well, that's oversimplifying it a tiny bit, but essentially, roughly, if you looked within the source code of an operating system that has support for a heap, you'll find code in there that actually makes up the heap. So this means that if you are compiling something under no operating system, like you are actually making an operating system, just as an example, you wouldn't have a heap and you would have to make one. So, what's the heap all about then? Well, the heap is just a big chunk of memory, and what can happen is you can slot different objects in and out of there, and objects can be removed at any point too. So basically what happens is your program says to the operating system, can I have X number of bytes please? And what the operating system will do is it will search through the heap, find an empty spot in the heap, and say, right, you can have this bit of the heap right here. If there are no spots, then the operating system will of course expand the heap. The heap is shared through your entire application. It's not shared through your system, and so each process will have its own heap. Well, that's generally in almost all operating systems. I mean, really, a lot of how the heap actually works depends on the operating system. It's just really the way you use it that's universal. So, unlike the stack, nothing gets automatically removed from the heap. So, while with the stack, when I exit a method, it pops those items off. With the heap, those items will stay there until we kill our process. And this is where memory leaks come from. You have to tell the operating system, right, I'm done with this piece of the heap right here, please remove it. And then it will remove that item from the heap. But if you don't free up that bit in the heap, it will stay there forever. So if you were allocating lots and lots of objects to the heap all at once, and you weren't freeing them, your program's memory usage would just go up and up and up, and that's how memory leaks happen. So before we look at how exactly we use this heap, let's quickly look at the advantages and disadvantages of both. So, the advantage of the stack is that it is fast. Seriously, in comparison to the heap, it is blazingly fast. Literally all it has to do is just put the value there and increase one number. That's essentially the big difference between the stack and heap, and why it's technically preferable to always write to the stack. But unfortunately it doesn't work out like that. Unlike the stack, the heap can grow and shrink, and can contain huge objects, whereas the stack is typically about 4 megabytes maximum size. And not only that, but of course, with the heap, objects don't automatically delete themselves. Now, that can be seen as a disadvantage if you're not careful, but that's also important if you want to create one object within one method, and then access that object after that method has returned, you have to use the heap. So essentially, anything where it could be any variable size, so we don't know its size in advance. So typically an array has to go onto the heap. Right then, let me now explain how we allocate and deallocate to the heap within our code. Now, this does vary a little bit between C and C++. So let me show you the C++ way first, and then I'll explain what the C++ way actually does, which will then bring us onto the C way of doing it. So, in order to allocate a new object to the heap, we write new, followed by our type of object, and constructor parameters after that. So, exactly like in C# or Java, we write new, and it will initialize this object. Now, what is different from C# or Java is that new returns a pointer, and that pointer points towards where that object is in the heap. So if I write this, then this will create an instance of myClass on the heap, so we have a myClass object sitting there on the heap. Then this new keyword here will create a pointer towards that myClass object. So we can then put that pointer into a local variable, so that pointer will go onto the stack, because it's going into a local variable. So, The pointer itself will get deleted when we leave the method. However, the actual object it's pointing to, that's on the heap, won't get deleted unless we free it. So, in order to delete it when we're finally done with it, we run delete, and we pass in our pointer. And then, whatever is implementing the heap will look at that location within the heap where that pointer is, and the heap itself will essentially keep track of how big all these things are. So, the heap knows exactly how big this object is, and exactly what chunk of memory it takes up. And so, it will just free it up. And now, any future objects we allocate can now fill the space. No memory leaks. Now, this is the code we write when we want to delete an object we put onto the heap. However, if we've initialized an array onto the heap, we'll get into arrays in a minute, then you need to write delete like this with square brackets. Otherwise, you'll most likely end up only deleting the first item in that array. Now, these new and delete keywords are specific to only C++. And these are the keywords you should be using in C++, because these make sure that you call the constructor and destructor on classes, which, well, C doesn't have classes, so that's why these aren't keywords in C. So, in order to look at how it works in C, we need to very quickly look at what the new and delete keywords actually do in the background. It's so simple. When you write the new keyword, what your program actually does when it's compiled and everything is it calls a method called malloc from the operating system. You might have heard of this before. Well, this is what new calls when it gets compiled. And this malloc method is provided by your operating system. Once again, oversimplifying a little bit there, but that's pretty much what's going on. So when we write the new keyword in C++, it will turn that into calling malloc, and of course, calling the constructor of our class. So let's look at this malloc method a little bit closer. It's really simple to use. It takes in an integer, and it returns a pointer. When you really think about it for a moment, you can probably guess what these two will be. The integer is how many bytes you want to allocate. So if I passed in 100, then our operating system or whatever will then find a space that has 100 bytes, and this method will return a pointer to the very beginning of that section in the heap. So then we can do whatever we want with that pointer and the 99 bytes that follow it. Now, it returns a void pointer, which I mentioned earlier. So this means that in order to use it, we would have to cast it to whatever type you want to put within those 200 bytes. So if I want to put unsigned shorts in there, which are 2 bytes big, then I would cast them to an unsigned short pointer like this. So C++ does that for you and works out the type at compile time based on what you write. But if you really wanted to manually allocate a block of bytes, then I suppose you could just call malloc. And in regular C, this is how you would have to do it. And freeing up memory within the heap can be done through free. And you just pass in your pointer again here. Right, let's talk about arrays. The most important thing you need to understand about arrays is that they don't exist. And what I mean by that is there's no array type. So I can't write integer array like this. No, there's no type for an array. The way you store an array is with a pointer, and that pointer points towards the very first item in that array. So, watch this. If I want to create an array with 100 integers on it, I would write this. Integer pointer, which will point towards the first item, then the name of the variable, and then new, see, allocating onto the heap, integer, and we want 100 of those. But C++ doesn't recognize this as an array. All it is just a regular pointer. So what if I want to access the second item in the array? Well then, I need to look ahead of the pointer by 1. And how do we do that? Remember, we use the name of the pointer, square brackets, and how far ahead we want to look. So, although this looks and feels exactly the same as using arrays in C# or Java, it's really not, because it's actually just a simple pointer. Now, that being said, there is a useful type that's the equivalent of a list in C# and the equivalent of an array list in Java. It's called a vector, and this is a managed array type, where it will automatically grow as you add items to it. Now, the vector type is inside a namespace, which is something we haven't had experience with yet, but it's essentially the same as in C# and Java. So in order to use a vector, firstly, we obviously need to have the correct header file included, because that's where the vector's outline will be, so that we can use this. But then, there are two ways we can access that vector, and this is very similar in C# and Java. So the vector is inside a namespace called standard, which is spelled like this. So if I want to access a vector, I'll have to write std, and then 2 colons, and this is essentially the equivalent of using a dot, except it works directly on static types. And then I can access our vector. Or, if I don't want to write this every single time we want to access something within the standard namespace, I can write using namespace std at the top, and this will automatically put this before anything that's in the standard namespace. So I won't go into vectors since this video is getting quite long and it's something you can easily Google, but you can add to it, remove from it, all of that, and it will automatically resize, and it isn't a fixed size. Just be aware about deleting vectors though. Now in this case, the actual vector itself is on the stack, so that means the vector will get destroyed when we return from this method, and the vector will destroy all of the items within it. However, you have to be careful here, because if the vector is full of pointers, it will destroy these pointers, but not what they're pointing towards. Don't fall into the trap. Right, let's quickly hop into strings, and then we'll blaze through the syntax and we'll be done. So strings are almost identical to arrays, in that they don't exist as a thing, as an actual type. However, there is a string class within the standard namespace that is designed to make working with strings easier. So, ignoring the standard namespace, a string is nothing but a character array. And in C++, as we know, an array is just a pointer. So if we write ABC in quotes like this will just create a character array with A, B, and C in it. This thing literally returns a character pointer. Well, not quite. It actually returns a constant pointer like this, but we can just cast that to a normal pointer. Now, unlike arrays where we have to just know how big they are and keep track of how big they are, strings, or more specifically character arrays, typically end with a null character. So that means that right at the end they have a character that's just 0. And that is quite important, because that means that if you pass your string to some external library, it will generally expect to see a null character at the end of your string. That's how it will know that it's hit the end. Now, when we use a string literal like this, of course, it automatically does that. So no need to worry about this. But if you're playing around directly with the character arrays, you have to be aware of this. This is also how the strlen function works. There's a function provided in the standard library that tells you how long a string is. And all it is just a simple while loop that counts up until it hits a null character. And this is essentially that strlen function right here. Just return I and you've got it. Alright, let's finish this up. As I'm writing this script for this, I'm becoming more and more aware of just how long this is getting. Now, there's also a class called string that's provided in the standard namespace under include string. And it's designed to make working with strings much easier. So that has concatenation and all sorts, which you obviously can't do with an array. Once again, Google will be your friend there. Right, that's all the difficult stuff. Let's blaze through some syntax points, particularly classes. So defining a class is essentially the same, but within the class is a bit different. Instead of putting the protection level directly on the members, like this, you have to move it above like this, and this will make any members below it public. If I then want to make these two private, I would write this, so I now have public and private members. Now inheritance is a bit different too. There's no such thing as an abstract class and an abstract anything, they don't exist. But you can declare virtual methods within a class. And you don't need an override keyword to override the method in the inheriting class. We just write exactly the same method name and this would override the base one. Now, in a proper program, of course, we obviously wouldn't be putting the actual code here, we would be using header files. But this is just to demonstrate. Now, when you do inherit from a class, you write a colon and write the word public followed by the name of the class. If you write the word private, it will do a sort of half inheritance. So this class is inheriting from this class, but no one else can see it. So you can't cast this class to the base class like you normally could. It's kind of like an invisible inheritance. Just don't use it. There's discussion about it on Stack Overflow, linked below, amongst a bunch of other discussions that I think are quite good to read when you're getting into C++. Right then, that's it. Yeah, that syntax section was quite short, but we already covered pretty much all of the syntax. Now, one thing that I did miss out was references. So, with a pointer, you write a star after the type. With a reference, you write an ampersand after the type. Basically, a reference is the same as a pointer, except for the fact that you can't actually change the reference itself. It will always point towards a given object. There's another article down there about references too. And that's it. Thank you for watching this video. Of course, be sure to leave a like if it was helpful, and comment if, well, you have any comments. Bye.